Solving exponential and logarithmic equations. First, we're going to start with some exponential equations. Now, with these two relatively simple examples, what you're going to want to do is isolate the the exponential expression first. So I'm going to add the 3 to both sides. So I'll have 4e to the 2x equals 5. And then I will divide both sides by the 4. So I'll have e to the 2x equals 5/4. And then from here, you can either convert it over to natural log form or to log form, or you can do like take a natural log on both sides, and then of course when you do the natural log of e, those just cancel each other out, really. They undo each other. So then you have 2x equals a natural log of 5/4. And then the natural log of 5/4 you'll get from the calculator, and then divide by 2. Well, you can also write this if you wanted an exact form. You can write that as 1/2 times a natural log of 5/4. When you do that in the calculator, you get approximately 0.11. All right, let's look at the next one. Same thing, we want to isolate the exponential expression, so I'm going to add the 4. So I'm going to have 2 times 3 to the 2t minus 5 equals 15. Divide both sides by 2, so it's 3 to the 2t minus 5. Let's call that 7.5. And then we can either just convert it over to log form, or you can, like I said, like take a log on both sides. And then this time I'm going to do a log base 3, because log base 3 of the 3 to a power is going to undo that 3 to the power. So then it just becomes 2t minus 5 equals log base 3 of 7.5. So the log base 3 of 7.5, you can get that from your calculator, or you can do the change of base formula, but we're going to add 5 to that. So it's 2t equals 5 plus log base 3 of 7.5. And then we can divide everything by 2, or you can also just do something like let's call it 5/2 plus 1/2 log base 3 of 7.5. So you could write that as your exact answer if that's what you wanted, or you can do all that in your calculator and get the approximated value is 3.42. Oh, come on. Let's take a look at number 3. Now you'll notice here this one's unusual because you have two exponential expressions. You've got the one with the base of 5 and the other side with a base of 6. So there's not really anything that you can do to isolate the exponential expressions. Besides that, you have two of them and they have different bases. The approach that I'm going to take here is I'm going to take a natural log on both sides. I could take a log base 5 to both sides or log base 6 to both sides, and I'd end up with the same result, although the process will be slightly different. But I'm going to recommend that if you have this situation where you have two exponential expressions with different bases, just always take a natural log of both sides. It's a fair choice to make here. So we're going to have natural log of 5 to the 2x plus 1 equals natural log of 6 to the x minus 2. Now I'm going to use the power property. I'm going to put that 2x plus 1 to the front times natural log of 5 equals x minus 2 times the natural log of 6. Now here's what's a little bit crazy. We are going to distribute that natural log of 5 on that side. We'll distribute the natural log of 6 on that side. You might be wondering why we're going to do this, but you'll see why in a second. So it's 2x times natural log of 5 plus natural log of 5 equals x times natural log of 6 minus 2 natural log of 6. Now you'll see that I have this expression, this term has an x in it, and this term has an x in it, and the other two terms don't have an x in them. So I'm going to put all the terms that have an x on the left-hand side. I could put it on the right, doesn't matter, and everything else on the other side. So I have 2x natural log of 5 minus x natural log of 6, and then this natural log of 5, I'm going to put that over. So I'm having minus natural log of 5 minus that 2 natural log of 6. Now it's not pretty, but it's all legal. So now these two terms on the left-hand side both have an x. Let's take that x out. So then I'll have 2 natural log of 5 minus natural log of 6 equals the negative natural log of 5 minus 2 natural log of 6. Now I'm going to divide both sides by, I'm just going to write that down, divide both sides by that 2 natural log of 5 minus natural log of 6 by 2 natural log of 5 minus natural log of 6 in order to isolate the x. So now I have x equals negative natural log of 5 minus 2 natural log of 6 divided by 2 natural log of 5 minus natural log of 6. Now, if I wanted the answer to be exact, then this is it. This is where I would stop. Like I said, it's not pretty, but it's accurate. Of course, if I put all that in the calculator, I'm going to get approximately negative 3.64. You're just going to want to pay attention to whatever the instructions are. If the instructions say exact value, you have to give that ugly business as the fraction. If it says approximate, then you can go ahead and find the decimal. All right, let's take a look at example number 4. Now, I haven't said this yet, but if you are not writing these examples down, I highly suggest that you pause the video and write down the problems. And once I get you going with the problem, then maybe you try to finish it. Pause the video and you try to finish it, and then unpause to see if you're getting them accurate, you're getting them correct. So this is another one that we've got two exponential expressions here. We've got the e to the 2x and the 3e to the x. There's not a whole lot you can do to isolate them, but what we actually have here is a hidden quadratic. I know you love those. And I know it's a hidden quadratic for a couple of reasons. I have three terms. That last term is a constant. And then if I look at the term in the middle, that e to the x, compared to the term in the front, the e to the 2x, e to the 2x can actually be written as e to the x squared. So the exponent on the front term is actually twice the exponent in the middle term. So here's how we can set this up. You don't have to do it this way, but you might like it. We're going to introduce a new variable. We're going to let u equal e to the x. And now I can rewrite this problem as u squared minus 3u plus 2 equals 0. And now we can just factor this in terms of u. So it's going to be u minus 2 times u minus 1 equals 0. So u equals 2 and u equals 1. But I'm not trying to solve for u, I'm trying to solve for x. So I'm going to back substitute. So it's going to be e to the x equals 2 and e to the x equals 1. And now you can just convert these over to log form, and this is going to be x equals natural log of 2, and over here x equals the natural log of 1. And again, if they wanted the exact value, then that's what you would give, natural log of 2 and natural log of 1. If you wanted the approximate value, then just put these, I'm sorry, you couldn't give that as natural log of 1. Oh, I take that back. Natural log of 1 is 0. Everybody knows that. So you would have to write x equals 0 for that one. And then natural log of 2, you can also do the approximate value for that, which is about 0.69. So you can either give 0.69 and 0, or natural log of 2 and 0, depending on the instructions, if they say exact value or approximate value. Now, let's take a look at number 5. And again, pause the video, copy down the problem. Now, this is one looks a bit crazy. You've got the 2 to the x. You also have a 2 to the negative x. This is actually another hidden quadratic. Hidden quadratic. Now, it doesn't really look like it, but let me do a little bit of rearranging here. So let's call this 4 to the 2x, and I'm going to call that 8 times 1 over 2 to the x, and then minus 33 equals 0. So one clue that it might have a hidden quadratic is that you have the three terms and that the third term is a constant. But the whole thing about the exponent and the front term being twice the exponent, it's not really following that rule here, but watch this craziness. Watch it. This is like total math magic here. I'm going to multiply the entire equation by 2 to the x. And you're thinking, what? Why? Well, you're going to see in a second. So if I do 4 times 2 to the x times another 2 to the x, remember when the bases are the same, you add the exponents. So it's going to be 4 times 2 to the 2x. And then that 2 to the x, here, I'm doing this right here, 2 to the x times the 8 times 1 over 2 to the x. Hopefully you can see that the 2 to the x's, those are just going to reduce down to 1. So that's just a plus 8. And then we're going to have the 2 to the x times the 33. I already did that one. So 2 to the x times the negative 33. So that's just going to be a minus 33 times 2 to the x. Well, this is strange. That negative 33 is no longer the constant. Watch this magic. I'm going to rearrange this. That's going to be 4 times 2 to the 2x minus 33 times 2 to the x plus 8 equals 0. Do you see the hidden quadratic yet? Well, we had to do a little bit of manipulation to get there, didn't we? We have our three terms. Our third term is a constant, and the exponent on the middle term is half the exponent on the first term. So if you want to do that, introducing the u variable, we can do that here. We can let u equal 2 to the x. You're always going to pick that middle term for the u value. So now I have 4u squared minus 33u plus 8 equals 0. Let's factor that. It's a quadratic. That factors as 4u and then a u and then an 8 and a 1, and those are both going to be negative. That works out there. So we're going to end up with a u equals 1/4 and u equals 8. But again, we're not solving for u, we're solving for x. Let's back substitute. We have 2 to the x equals 1/4 and 2 to the x equals 8. Hopefully you see where this is going to work out kind of pretty here, because 2 to the x, well, 8 is 2 to the third. So when the bases are the same, the exponents have to be the same. So x equals 3. It's a little sloppy. Let me try that again. X equals 3. There we go. And then the 1/4, we can rewrite that as 2 to the negative second. Again, bases are the same, so the exponents are the same. So here we have a nice pretty answers, -2 and +3. All right, here we are on number 6. I gave you a little clue on this one. This is a doozy. Make sure you pause the video and copy down the question. Now, there's another hidden quadratic in this one, but it's really difficult to see it the way that it's written. So let's do a little bit of manipulation like I did in the previous problem. First thing I'm going to do is I'm going to multiply both sides by the 2. So I'm going to have 5 to the x minus 5 to the negative x is equal to 6. We can set that equal to 0. So I'm going to have 5 to the x, and I'm going to go ahead and change this to a 1/5 to the positive x minus 6 equals 0. Starting to look a little bit like the previous problem. Let's go ahead and do that wild, crazy magic trick where we're going to multiply everything through by the 5 to the x. And you could reason here that, oh, I don't like the fraction. I don't like having that 5 to the x in the denominator. So let's multiply through to get rid of it if you'd like that. So 5 to the x times 5 to the x, the bases are the same. You add the exponents. That's 5 to the 2x. And that's going to reduce down to just 1. And then we're going to have this minus 6 times 5 to the x equals 0. If I rearrange it, I have 5 to the 2x minus 6 times 5 to the x minus 1 equals 0. There, once again, is our hidden quadratic. So we can let u equal 5 to the x. So now I'm going to have my equation is u squared minus 6u minus 1 equals 0. So we have a quadratic. We need to factor it, or solve it, rather. Unfortunately, this one doesn't factor. So what do we have to use? That's right, the quadratic formula. So we're going to have here u equals, let's go ahead and write down, negative b plus or minus the square root of b squared minus 4ac all over 2a. So u equals 6 plus or minus the square root of negative 6 squared minus 4 times 1 times negative 1, all divided by 2. So now we're looking at 6 plus or minus the square root of, just jumping ahead a little bit, that's going to be the square root of 40, all divided by 2. 40 has a perfect square in it. That's going to be 6 plus or minus 2 root 10, all divided by 2, and we reduce that. And then, of course, you can split that up and call that 3 plus or minus the square root of 10. And all of that is equal to u. But we weren't trying to solve for u, we were trying to solve for x. So if we back substitute, we're now looking at 5 to the x equals 3. Let's go ahead and call these two different things. 3 plus the square root of 10, and also 5 to the x equals 3 minus the square root of 10. What? This is still wild. We've got an exponent that's a variable. We've also got a radical here. What are we going to do? Well, we're going to do the same thing that we've done before with exponential expressions. I do want to point out here that if you were to work out whatever 3 minus the square root of 10 is, hopefully you understand that that's going to be a negative value. And 5 raised to the x equals a negative value? What? That's not a thing. So we actually can rule out and throw away that equation because you're not going to get a solution from that. So now we're looking at the 5 to the x equals 3 plus the square root of 10. Whatever 3 plus root 10 is going to be a positive value. So the exact answer here would be, just to convert this over to log form, would be, well, if you'd like, we can do a log base 5 on both sides and kind of put some parentheses there. And then the log base 5 of 5, those undo each other. So now we have x equals log base 5 of 3 plus the square root of 10. So that is the exact value. Are you super excited about how pretty that is? If you wanted the approximate value, just type that into your calculator. You can do the change of base formula, and you're going to get about 1.13, and that is the approximate value. And there you have it, either log base 5 of 3 plus root 10 or about 1.13. Off with exponential, let's solve some logarithmic equations. Let's start with a simple one first. So just like with the simple exponential, we're going to isolate the logarithmic expression here. So I'm going to subtract the 5. So we're going to have 2 natural log of x equals negative 1 and divide by 2. So natural log of x is equal to negative a half. And then here you can convert that over to exponential form. I like to call that the swirl. So that's going to be e to the negative 1 half is equal to x. If you wanted an exact value, you can call that 1 over e to the 1 half. If you really want to be maybe a little fancy, you can call that 1 over the square root of e. Impress all your friends. If you wanted the approximate value, just work that out in your calculator. You're going to get about 0.61 approximately equals x. So again, that would be your exact value, and the 0.61 would be your approximate value. Now, one thing that you have to remember about solving logarithmic equation is that the argument always has to be positive. This means that once you solve, you need to check for extraneous solutions. So if I go back up here, 0.61, it is a positive value. And if I check up here, I will be plugging a positive value into the argument of that logarithm, and that's totally fine. So that's why that one works. Let's take a look at number 8. Now here I have 2 logarithms on the left-hand side and 1 on the right-hand side. I'm going to use my properties of logarithms to condense this down. So this is an addition sign, so this is going to be my product property. So we're going to call this natural log of x minus 2 times 2x plus 3 equals, and I can use the power property and use that power property, and call that natural log of x squared. And you remember this sort of equality property. If you have log of something quantity equals log of a different quantity, then those two quantities must equal each other. So now I'm actually going to go ahead and FOIL that here. So we're going to have 2x squared. Let's see, that's going to be a plus 3, and it's going to be a minus x minus 6 equals x squared. So let's set that equal to 0 so that we can solve. So if I subtract the x squared, I'm now going to have x squared minus x minus 6 equals 0. That's an easy one to factor. X minus 3, x plus 2 equals 0. So we're going to get x equals 3 and x equals negative 2. So you might be feeling pretty good at this stage, but actually this negative 2, if we check it, we could go back up to say here, if you try to plug in a negative 2, if you're looking at 2 natural log of negative 2, that's no good. You can't plug a negative value into a logarithm. So that right there is enough to throw out the x equals negative 2. That's not a solution. You'd also going to want to check the 3. Remember, it's not just because the value is positive, it's whatever makes the argument positive or negative. So if you check the 3, you can plug 3 into the natural log of x. If you plug 3, I'm not sure if you can see my mouse here. If you plug a 3 into that expression, it's going to stay positive. If you plug a 3 there, it's going to stay positive. So x equals 3 is our one and only solution. All right, let's take a look at number 9. So this is some craziness right here. We've got an entire logarithm underneath the square root, and then of course we've got just the x underneath this cube root. Well, let's go ahead and use our properties of exponents, we could say, to change that to log of x to the 1/3 equals, let's go ahead and leave the square root of log of x, and then let's move that 1/3 down to the front. It's always a good idea to move those exponents there before you do anything crazy and rash. Like what I'm going to do right here is, oh my gosh, I'm going to square both sides. So on the left-hand side, I'm going to have 1/9 log of x. So just go ahead and do a square like that. Equals, and then that square and the square root on that side, those are undoing each other. So that's log of x. Doesn't seem like it's any prettier, but what I can do now is I can set it equal to 0. So it's 1/9 log of x squared minus log of x equals 0. And now I can take out the greatest common factor. So if I take out a log of x, I'm left with 1/9 log of x minus 1 equals 0. Now I can say log of x is equal to 0 and 1/9 log of x minus 1 is equal to 0. So I'll add 1 over here. So it's going to be 1/9 log of x is equal to positive 1, multiply both sides by 9. I've got log of x is equal to 9. And so this, when I convert it over to exponential form, this means 10 to the 9th power is equal to x. Remember, with the logarithm, if the base is not written, the base is understood to be 10. And then over here, log of x equals 0. That means 10 to the 0 is equal to x. Well, of course, 10 to the 0 is equal to 1. So one of your answers is 1, and the other answer is 10 to the 9th. We should go back up and check for extraneous solutions. Well, these are both positive quantities, and when you plug those into the logarithms, they're still going to be positive, so they are both solutions. All right, here's number 10. Now, this one is a little unusual, and I'm not crazy about the fact that it doesn't state that you want to do this with a graphing calculator, but we are going to do this with a graphing calculator, or a graphing utility. Sometimes they say a graphing utility. So what I'm going to do is I'm going to go to my calculator. I'll pull it up in a second. And in y1, I'm going to use my T84. I'm going to graph the natural log of x. And in y2, I'm going to graph x squared minus 2. That's just a parabola. And we're just going to calculate those intersections. So I'm going to pull up my calculator now. All right, so I've got my graphing calculator. So in y1, I'm going to just graph natural log of x. And then in y2, we're going to have x squared minus 2, like so. Let's just do a zoom 6 just to get our standard viewing window. And we can see that they intersect. It looks like they intersect twice. It's not entirely clear. I'm going to change my window a little bit. Okay, so just change my window a little bit so I get a different view. And we can definitely see for sure that they intersect in 2 places. So I'm going to go into the Calculate menu, second trace. I'm going to choose Intersect, option 5. First curve, the cursor is on the first curve. I can see in the top of the screen that it's on the natural log function. I'm just going to press Enter because they're asking me if that's the first curve. And then the cursor jumps to the second curve and it's asking me, is that your second curve? Yes, it is. Press Enter. Where's your guess? And if you have more than one intersection, the guess is very important. So I'm going to put the cursor close to where it looks like they're intersecting. I press Enter, and then it gives me this decimal about 0.138. And then we'll do it again for the other one. So second trace, intersect, first curve, yes, second curve, yes. And then for the guess, you can either use your arrow key or you can jump over. It looks like it's about 1.5, so you can actually type 1.5 from your keyboard. Press Enter, and there's my intersection at about 1.56. So let's write that down. So they wanted these answers to 3 decimal places, so x is approximately 0.138 and approximately 1.564. Voila.